Welcome to the session 2 of module 2. Here in this particular session, we will be discussing about more operators that can be used with binary coded GA. Including that, we will also discuss some simulations on mathematical functions for which the optima is known to us. So therefore, the outline of this particular session is decided as we will be talking about the selection operator, thereafter the crossover operators and the mutation operators. So various types of operator we will discuss, and then we will be showing some application using binary coded GA. And at the end we will close this module 2 on binary coded GA. So before we move to the operators, different types of operators, let us have a recap of our previous session. In the previous session, we started with binary coded GA and we implemented and discussed the binary coded GA with the help of the generalized framework. Using that generalized framework, we took a problem of Rosenbrock function, and on this function we started with the working principle of binary coded GA. Since in binary coded GA we use binary string, so first we saw the solutions representing using binary string. When we have binary string, we can represent the decision like 0 or a 1, yes and a no, on and off. Similarly, we can also use binary string for discrete variable as well as for the integer variable. We took an example of real variable where we took a binary string length of 5, and accordingly we showed how this 5-bit binary string, we decoded it, and using the scaling formula we got the value of a real number. That real number we use the lower and upper limit and put in the scaling formula, and we get the value of the real number. There was a parameter called precision that also we discussed, and we found that if suppose we want more precision, in that case we have to increase the length of binary string. Thereafter, in the working principle, we took that Rosenbrock example and then we started with the selection operator. Now in this selection operator, we discussed binary tournament selection and we selected those solutions to making a matching pool. That matching pool then was used for the crossover and mutation operator. We discussed single point crossover operator and bitwise mutation operator. Afterwards, since the crossover and a mutation operator, they generated a population which we refer as a offspring population, and we also started with the parent population. So since we have two population that are parent and offspring population, so we selected the best solutions from them. So we used mu plus lambda strategy to select the best solution for the next iteration. In this particular process, we showed how the solutions were improved. Some solutions were improved using crossover and mutation. Some solutions have generated with the bad value of the fitness. The same example we took and we showed for the graphical example. So just for one generation, we understood how the initial population was generated, and using the selection followed by crossover and mutation operator, we get the solution. So we found that the solutions in one generation started moving towards the optimum solution. Now let us begin with the more operators for a binary coded GA. In the previous session, we discussed the selection operator. As a recap, we know selection operator, the purpose of selection operator is to identify good and above average solutions. And when we are doing this process, we eliminate bad solutions and make duplicate copies of the good solutions. So in this case, we are emphasizing the good solution and removing the bad solution. So overall, we are making a pool. As you remember, that selection can be done before the variation operator and after the variation operator. When we perform before the variation operator, this selection process generally referred as reproduction or selection. Thereafter, if we perform selection after variation operator, so the main purpose is to find out best solutions that will be chosen for the next generation population. This stage is referred as survival or the elimination. Sometimes it is also referred as the environmental selection. In order to perform various kinds of selection or using different kind of selection operators, we have a list. For example, we can use fitness proportionate selection, we can use tournament selection, ranking method, and there are few more. So we will be focusing on few important selection operator in this session. Let us begin with fitness proportionate selection. Now here, when we select a solution, before that we find the probability of solution. Now the probability of a solution, and sometimes we also call it as a individual. So the solution, the probability of a solution we calculated with the help of the fitness value. So Fi here represents the fitness of the solution, and this fitness is divided by the summation of fitness of all the solution in the population. So in this particular formula, what you can realize that the value of Pi depends on what is the value of the fitness of a solution. If the fitness is large, in that case the probability of selecting that solution is large. So from this explanation, you can get to know that I can use the fitness proportionate selection operator for maximization problem. This operator is also known as roulette wheel selection operator. So there are different names. Some people refer as a fitness proportionate selection method, and some refer it as a roulette wheel selection method. So let us see how it works. So here we have taken the same population that we have used with an example of binary coded GA. Now the fitness of all these solutions have been taken. Now here it is important to note that when we have to perform any selection, we don't need any binary string or the decoded value of the binary string or the value of x1 and x2. What we need is only the fitness value here, which is mentioned in the column number 2. Now in column number 3, we have mentioned the probability of each solution. So let us see how we can calculate the probability of each solution. So on the right hand side, we will find the probability for this solution. Before that, we have to take the sum of all the fitness. So if you look at this particular column number 2, if we take the summation of all these fitness value, you will get this sum. This sum is the summation of the fitness of all solution. Now the probability of solution 1 is the numerator, we get the same fitness of a solution 1 here, and the denominator is the summation. When you divide it, you will get the probability as 0.0041, which is you can see in the third column of the table. Similarly, if we follow the same procedure, we can find the probability of selecting solution 2 as In the numerator is the fitness of a solution 2, which you can see here, and the denominator is the summation of the fitness. When we find it, the probability is 0.1471. So this process will be followed, and we can find the probabilities of all the solution by dividing the fitness with the summation of all the fitness. Now it is here in the last column, as you can see, we are finding this capital Pi, which is the cumulative probability. This cumulative probability, we use it to select solutions. So let us see how we can implement fitness proportionate selection operator. Now in the figure on the right hand side, on the top, you can see this is solution 1, 2, and all the solution till 8, all of them are given. Now the rectangular boxes are shown here that represent the portion or the probability of the solution. So corresponding to the probability, these rectangles are shown here. On the x-axis, we have the cumulative probability, which is capital Pi. So how we are going to select? We will generate a random number Ri between 0 to 1. Once we generate it, we can find where is the counter. So you can see this particular counter. So this counter will say that we are going to select a solution. So let us see how it works. So in this case, first of all, we are going to calculate the probability of each individual. Then we are going to find the cumulative probability. Now we are generating random numbers. So assume that the first random number is this. So if you say 0.07218 is your first random number, so where you will be looking? You will be looking at the cumulative probability. So it will be coming here. Since it is coming here, so we are going to select solution number 2. Similarly, if suppose you have the random number R2 as given 0.68799, this says that the counter will be here. In this case, we are going to select solution 8. Now by using this, we have already selected solution number 1 and solution number 2. Now we have to select few more solutions. Now in this, when we are going to follow the same procedure, let's assume that these are the random numbers which are generated in a sequential manner. When we are generating it, so the solution like 7, 3, and again 7, then one more time 7, 8, and finally 8. All these solutions will be selected. Now it is we have to remember here that we will be performing the selection operator such that we should select the solution equal to the number of population, that is n. So let us copy all these solutions now. So you can see that when we select a solution, solution 2 will get 1 copy, solution 3 will get 1 copy, solution 7 will get 3 copy. Similarly, solution 8 will get 3 copy. What you can understand here is these two solutions, especially 7 and 8, are the super solution. So we will discuss what is super solution in the following slides. The another kind of selection operator we have is the stochastic remainder roulette wheel selection operator. In this selection operator, we calculate probability of each solution using the formula used with fitness proportionate selection operator. So the formula is going to remain the same. However, what we will do is we will multiply the size of the population, which is n, with the probability of each individual. So here the same table we have drawn. So we have index, we have fitness values, and these are the individual probabilities. So we use the same formula and we get the same probabilities. In the last column, you will see that we have multiply the population size into the individual probability. So this is the number which we get it. What this selection operator says that we assign a number of copies to the solution based on the integer value of the product of NPI. It means that if we take a solution number 1, so the value of NP1 is 0.0329. Since at the integer value it is given 0, so this means that we do not select this solution. Now let us look solution number 2. Here the value of NP2 is 1.17. In this case we will select only the one copy of this solution. Similarly, the solution 3, so if we are going to follow, so let us look into the table. So here the solution 2 we will get 1 copy, solution 3 we will get 2 copies, solution 7 we will get 1 copy, and solution 8 we will get 3 copies. So similarly we are going to get that many number of solution. If we count all the number of solutions, so actually we selected 7 solution, and you remember that our population size is 8, so we have to select one more solution. In this case we use the fitness proportionate selection operator using the decimal values. So here the same table we are drawing, in which the NP we have written. Now in this case you remember that these are the solutions, the copies of the solutions we have already selected. So we are going to remove them. So we will be dealing only with the decimal places for all the solutions. So you can see that all the decimal values are given in this table. Then afterwards we will find the cumulative probability as we have found it out. You can see the summation is 1. Now similar to the fitness proportionate selection method, we are going to generate a random number, and wherever it is lying the solution will be selected. So let us assume that we have a random number as 0.76335. If you look this particular value, so the counter will be coming here. So in this case we will be selecting solution number 6. So we selected 7 solutions earlier. Now by generating a one random number, we selected the one more solution. Now the overall solution is equal to the size of the population. Now here when we are performing the stochastic remainder roulette wheel selection, you can realize that the first part of this operator is deterministic. It is because the numbers which we selected is based on the factor or the multiplication NP. So since the probability was high, so this solution got 1 copy, 2 copy or 3 copies. That makes the first part of this operator deterministic. The second part, which we have just now discussed with the help of this random number and the decimal values, you can see that this is the stochastic in nature. Since the first part was deterministic, this operator is considered as less noisy than the fitness proportionate selection operator, in the sense of introducing less variance in its realization. We have another kind of selection operator which is known as stochastic universal sampling. In short, we say it is called SUS operator. Now in this operator we are again going to find the probability of each individual. The formula given in the fitness proportionate selection will be used, and thereafter we calculate the cumulative probability for each solution. Now in this selection operator, we are going to create only one random number. So let us see how this random number is going to help us. So since we are going to calculate just one, then we are making the n equispaced number. So let us see how. So we generated a random number. The second number will be r plus 1 by n. So n is the population size. So accordingly we have divided our range into equispace, and that depends on the size of n. Let us see how it is working. Suppose we have the random number as 0.40416, and if we calculate 1 by n, we get a value 0.125. It is because the size of the population is 8. Now since the value of a random number is 0.40, you can make it out that the counter will be here. So in this case we will be selecting solution number 3. In the next stage, what we will do is we will have a random number plus 1 by n. So this summation is going to give a value 0.52916. Now if you find where it is lying, so this is the counter where we will get. We can see the counter. According to that, the solution 7 is selected. So this way we will be following, and we can select the solution using SUS operator. Now here, when we will be performing these series of a number, we can get the numbers, or we can get the number after 1 plus n. Now once we have reached, so here you can note down that once we are going, our number is going more than 1, so we subtract 1, and the value which we get, we will be considering it. So it's like a circle, and then we follow. So these numbers tells us that we are going to select the 3 copies of solution 8, then solution 2, and then 2 copies of solution 3. Now there are certain limitations with the fitness proportionate selection operator. Let us see what are those. So domination of super solution. So this particular term we have used earlier. So let us see what it means. Suppose we are maximizing our fitness and we have 5 solutions with us. Now the fitness for each solution given as 10, 5, 70, 7 and 8. Now when we are comparing and we are finding the probability, you can make it out that the solution number 3, which has the fitness 70, which is a very big value as compared to the fitness of other solution, this solution will behave like a super solution, because this solution will get more number of copies and will become dominant over the other solution. You will realize that after few generation there will be only one type of a solution in the population. Another limitation is the slower convergence in later generation. So again we take the fitness of 5 solutions and we are maximizing it. So the F1, F2, F3, F4 and F5 are given here. Now let us compare them. Here when we are going to calculate the probability of each solution, you can realize that these values like 19, 21, 22, 18 and 20, all of them are very close to each other. This means that they are going to make a equal division on the cumulative probability scale. So when we are going to generate a random number and selecting the solution, you will realize that everyone will get the copy. It means that the selection operator is not performing anything and we are selecting the same solutions as we have earlier. So in this case you can realize that the selection operator will behave like a dummy because it is selecting all the solution given in the population. So these are the two limitations, where in one case we have super individual, in which one individual has the largest fitness or very large value of a fitness as compared to other. In another case, all solutions have very similar kind of fitness values. So what are the possible remedies to the problem? We can use fitness scaling. But when we use fitness, we have to perform some kind of a scaling to select a solution. In this case, we can use some kind of a ranking selection, and this ranking can avoid fitness scaling. We also have a tournament selection. So as we discussed in the previous session, we had binary tournament selection operator. So these tournament selection operators, they don't have any scaling problem. Let us move to the another type of operator, which is not behaves like a fitness proportionate selection. It is a tournament selection. Since we have already gone through it, let us have a generalized definition of the tournament selection. Now you can see that we have a tournament selection with the tournament size of k. So we are going to randomly sample the k number of solutions. So we have a large population, we sample k solutions, and then we select a solution based on the best fitness. So let us take an example here. Suppose in this problem we have 10 solutions with us. In these 10 solutions, let us choose, we have a tournament size of k. Now you may be wondering that earlier we discussed the tournament selection as a match between or tournament between the two teams. Since this concept has been used, we can simulate this particular operator for any number of tournament. So we are taking in this example k as a 4. So meaning that there are 4 solutions, they will be competing with each other, and the solution which has the best fitness will be selected. So these 4 solutions, suppose we have taken the 4 solutions, these are the randomly selected solutions and the fitness are given. Now for a maximization problem, if we ask a question, which particular solution is going to win this tournament? Since it's a maximization, you can make it out that this fitness is the maximum one, so solution 3 is the winner. Similarly, for a minimization problem, who will be the winner? Again, we can see the fitness and we know that the solution 6 has the less fitness, so we will select this solution. What is interesting about this operator? That whether it is a maximization problem or minimization problem, this operator can be used. Only the relationship we have to change. In the case of maximization, we will be looking for the fitness, for the more fitness, larger fitness. However, for the minimization problem, we will be looking for the least fitness. So if we change the relationship, we can use the same operator for both kind of objective functions. However, with the fitness proportionate selection method, you might have realized that the operator is designed for maximization problem only. If you want to use for minimization problem, then you have to use duality principle to convert minimization problem into maximization and then use it with the fitness proportionate selection method. Now often the size of the tournament we keep as a 2, and that's why we call this tournament as a binary tournament selection. So we have discussed it thoroughly in the session 1 how this binary tournament selection works. Only important point you have to remember that the number of tournament has to be done in such a way that we should select n number of solutions. We have operators for survival or elimination. We discussed this mu plus lambda selection scheme. It was easy to implement. In this selection scheme, we have mu number of parent population, and after performing say variation operator, we created lambda number of offspring solutions. So in this process, what we do here is we combine both of them. So combined population of parent and offspring solutions we took, and then we sort, and after sorting we select the best solution for the next generation population. Second type of selection scheme which we can think is the mu lambda selection scheme. Now in this case, the lambda should be more than mu, meaning we generate more number of offspring solutions than the parent solution. So in this case, we are going to select best mu solutions from the offspring population only. So here we are not going to involve any parent solution. Both the selection schemes supports elitism. Now elitism is a word, we use it when we keep good solution in our population. Now in the first scheme, you can realize that when we are combining parent and offspring population, we are not going to miss any of the good solution. In the case of mu comma lambda scheme, if the offspring solutions are not as good as parent solution, we may lose the best solution in this process. Now we have discussed various kind of selection operator, and we are free to choose any one of them. With the help of their limitations, we can make it out that which selection operator will be useful for us. Now we are moving to the variation operators. In this class, we will start with the crossover operator. Now generally, when we say crossover operator, we use more than one parent. So what is the basic difference between crossover and a mutation? You can realize in crossover, we need more than one solution to create new solutions. However, in mutation, we need only one solution to generate another new solution. So in crossover, we have a probability PC, which we referred as crossover probability. Theoretically, it says that if we are saying 100 times of PC, that many strings will take part in the crossover, and rest of the string will be copied as it is. If you remember the case which we have discussed in the last session, there were couple of strings which were just copied because the random number was more than the probability of a crossover. So those particular strings were copied directly, and rest of the strings based on the probability of crossover and random number, we perform the crossover operator. In this category, we have different kind of crossover operators. So let us begin with the single point. This crossover operator we already discussed. So in this case, what we do, we have, for example, parent 1 and a parent 2. We pick the random site here. I am using the different color coding so that we can understand, and we know that once we know the site, we are going to swap the tails, and with the help of color coding you can make it out that since we have red and a blue combination, we are generating new solutions. So those are referred as offspring 1 and offspring 2. The another kind of crossover operator we have, it's n-point crossover operator. What we do here is we choose n random sites, we split the site, and then we glue some part and we exchange some part. Let us see how it works. So here we will be discussing 2-point crossover operator. So in this case, we will be selecting two random site. So the first random site is given here and another random site is given here. What we will do is we will glue the corners and the middle part will be swapped. Now you can see in the offspring 1 and a 2, only this middle part is swapped and the tails and the front will remain the same. So this crossover operator can generate the offspring in this way. Now what you can see a little difference with respect to the 1-point crossover. Now using 1-point crossover operator, you may be changing one variable at a time, but using 2-point or 3-point crossover operator, you may be changing multiple variables at a time. Now remember that we used, suppose we have x1 and x2, we use some set of binary string, say 0, 1, 1, 0, 1, and we have 1, 1, 1, 0, 0. So basically both of these two strings, when we combine them, that makes a chromosome. So we have a chromosome string of length 10. So when we perform crossover using single point crossover, maybe x1 or x2 will change, but with 2-point crossover, both of the variables can change at a time. There is another crossover operator which is referred as uniform crossover. In this crossover operator, we select a string z, which is another binary string that is generated randomly. Let us see how it works. Say suppose you have parent 1 and parent 2, and we created this z string randomly. Now what it says that suppose we have 1 here, then we will be selecting the bit from parent 1 for offspring 1. If it is 0, then we will be selecting a bit from parent 2 for offspring 1. So let us see how. So in this case, you can see 1, if it is 1, then the offspring 1 is get the bit from the parent 1. If it is 0, then it is getting from parent 2. Similarly, for offspring 2, it says that if you have 1, then the bit will be taken from parent 2. If it is 0, then the bit will be taken from parent 1 for offspring 2. So in this way, there is a total random swapping of the bits for 2 parents, and that is going to create 2 new offsprings for us. Once we perform the crossover operators, we have different types of mutation operator. Now mutation operator introduce small random changes to a solution chromosome. It is because we perform mutation with a less probability. Now let us take the first mutation operator, that is local mutation operator. This is what we studied or understood in the last session. So here one random bit will be flipped. Flip means that if it is 0, it is converted to 1, and 1 is converted into 0. Suppose we have a binary string and randomly we pick the 4th position. Now in this case, we are going to convert this 0 to a 1, and this is the local mutation. And at a one time, we are changing just one bit throughout the string. Another kind of mutation operator is global mutation operator. So each bit, in this case we are going to take each bit in the binary string. So each bit will be flipped independently with a given probability Pm. It is also called as bit mutation rate, and which is often we take it as a 1 by n. Now n is the length of the chromosome length. Now suppose we have a binary string, and for this particular bit we generated a random number. If this random number is smaller than the probability of a mutation, so currently probability of mutation is 1 by n. If this probability is, if the random number generated is less than the probability, we will perform the mutation. So in the first bit, suppose the random number was more, similarly for second, but for the third, the random number was smaller than the probability of a mutation. So this is going to be, so this particular bit will be flipped. Similarly, we check for all the bit one by one independently, and suppose this is the bit, this is going to change, and then the other one. Now you will realize that the flipped bits are changed. So 1 has been changed to 0 and 0 is changed to 1. So that makes the random change in a binary string. So in the case of local mutation, we are changing just one bit per string. However, in the case of global mutation, we are changing the bit as per the random number smaller than the probability of mutation. Now let us start the simulation and application of binary coded GA. So till now we have understood how binary coded GA works, and there are different kind of operators which are available. Now the operators which we have discussed that are limited in number, when you look into the literature, there could be more types of crossover operator, mutation operator, and sometimes the selection operator. So the researchers are keep on changing the kind of operators that suits their problem. Now let us begin with the simulations and application. So the first function we have taken as a Rosenbrock function. You remember that this is the same function we have used to understand the working principle of binary coded GA. In the generalized way, the Rosenbrock function can be written in terms of n number of variable, and the formula is given here. All the variables will be lying between -5 to +5. In the figure which is shown on the left hand side, it is shown only for the two variables x1 and x2. So the optimum solution for Rosenbrock function is that the solution will always have a value 1. So all variables are going to get 1, and the function value at the optimum solution is 0. We have used binary coded GA. So in the generalized formulation, in this step 2, there are a lot of input parameters which we have to set. So this particular slide will tell how many parameters we have to fix before we start the binary coded GA. Let us take an example of two variable Rosenbrock function. The population size is set as 40, and we allow large number of a generation to see the progress. So here we have set the number of maximum number of generation 200. Currently we pick x1, so binary string length for x1 is 5, binary string length for x2 is also 5, and the total length of binary string is 10. So 5 plus 5 will make 10. Since Rosenbrock function has many local optimum solution, so we are keeping the probability of crossover high, which is 1. The probability of a mutation we have taken 1 by n. This n should be small n because the small n tells the number of variable. So in this case, since the number of variables is 2, so this will become 0.5. Binary tournament selection operator is used for selection before variation operator. Thereafter we perform single point crossover operator. For a mutation we perform bitwise mutation, and finally for selecting good solutions from parent and offspring population, we are taking this strategy mu plus lambda strategy. So let us see how this binary coded GA work here. So here in the picture you can see this is generation 1. So all the blue dots are the randomly generated solution in the plane of x1 and x2. So we make sure that the solution should generate within the range of x1 and x2. Now let us see how this simulation work. Now here what you can see that solutions were randomly distributed, and with the number of generations these solutions now moving towards the optima. So, the red dot here is the optimum solution as we know, and there are many local optimum solution. Now, at this stage you can see that the solutions are not improving much. It is because we have taken a small binary string length for x1 and x2. Now, since these solutions are here and there are small changes, you can observe that there is no change. It is because crossover is actually not generating any good or any new solution. It is only the mutation operator that will help us to generate a solution close to the red dot. So, let us wait for the generation number 200 and see how close we can reach. So, this is the blue point which is closest, and that remains the same. Now, let us look the progress. So, the progress means that the x axis will be the number of generation and y axis is the best fitness. Now, in this case you can see the improvement in the solution, it's drastically it reduces in the early generations, and thereafter after 23 generation the improvement, there is no improvement in the fitness. So, the best fitness, this is and the same situation we have observed when we shown the convergence plot for one dimensional landscape, that the GA will improve its fitness very quickly. However, it will take some time to converge to the optimum solution. Let us take another case. Now, here the number of variables remains 2, population size remains 40, number of a generation 200, binary string has been changed now. Now, you remember that if we are going to take a larger size of a binary string, then the precision of x1 will be higher. So, for x1 we are taking binary string length of 10, for x2 the binary string of length 10 is taken. So, total is 20. The crossover probability is kept same, which is 1, mutation probability 0.5, and we use the same set of operators such as binary tournament selection operator, single point crossover, bitwise mutation and mu plus lambda strategy. For this case we generated a random population. This population, these members are different from the previous case. So, these are generated in a plane of x1 and x2. Let us see whether changing the L1 and L2, the binary string, will help us to improve the solution or not. Now, these are the simulations. So, the solutions were generated randomly throughout the range of x1 and x2. In few iteration, that is less than 25 generations, the solutions are already close to the optimum. Now, the distribution of the solutions you can see, because there are a lot of local minimas, but there are certain solutions, as you can see, that these solutions are quite close to the red dot, which is the optimum solution. Now, one particular solution has already reached very close to the optimum solution, somewhere in the 90 generation, and let us see that in 200 generation can we get the optimum solution. Now, you can see another solution is generated close to the optimum, and rest of the solutions are also improving, and slowly these solutions are moving. It is because we have selection operators. Now, the solutions, since these are moving, we are expecting that at the end one of the solutions should generate. So, now you can see that we have increased the string length for x1 and x2 from 5 to 10, but still the solution, there is no solution which has converged to the optimum solution. Let us see the progress. In this progress, the number of generation versus best fitness, you can see how quickly GA, binary coded GA, has reached to the value close to 0, and then there is and then the best fitness remains the same. the other solutions are improving. Somewhere at 150 generation, there was a improvement in the fitness. So let us see one more time. So close to 150, we will see little improvement. Yes, so here somewhere close to 150, we have a little improvement in the fitness. Now since we did not get the optimum solution yet, we increase the length of binary string for x1 and x2. In this case, the binary string length for x1 is 20 and binary string length for x2 is 20. So total chromosome string length is 40 now. We have taken the same two number of variables, population size, number of generations are kept same. Similarly, the probabilities and the operators were also kept the same as before. So this is the random population that is generated, and we will see the simulation for a larger binary string. Now again, the solutions are moving quickly close to the optimum solutions, and then in 25 generations we are already close to the optimum solution. Now we have to see whether binary coded GA can generate a solution on the red dot, meaning that binary coded GA can find an optimum solution for this problem when length of the string is increased. Now this blue point, as you can see, which is quite close to the red dot, which we have identified or the binary GA has found in say 80th generation. Other solutions are also moving. Now there are two solutions which are close to the red dot, and we have to see whether BGA can find a solution for us or not. Now slowly the other solutions are also moving from other directions. Now you have more solutions, so this red dot is surrounded by many solutions. So from this simulation, what we have identified, that since in the binary string we are increasing the binary string length, meaning we are increasing the precision for x1 and x2, the solutions are going closer to the red dot, but still it has not reached to the optimum solution. Let us see the progress now. So we have a drastic improvement here, and with the number of a generation, the best fitness in the population is keep on improving. So around just before 70 iterations, we found that the best fitness remains the same, and after few more generations, let's see one more time here. So somewhere close to 150 we generated, so BGA generated a solution quite close to the optimum solution. Till now, what we have solved for Rosenbrook function is two variable problem. If we increase the number of a variable, we will see how the performance of binary coded GA will change. In this case, the population size, number of generations are kept same. Since we want more precision, binary string length of 20 and 20 is used. So please note that here we have shown for x1 and x2. Similarly for x3 and x4, we have used 20 and 20. So overall binary string length or the chromosome string length is 80, not 40. So this is it is 80 for this particular problem. So probability is kept 1. Probability of a mutation is, again we kept it 0.5. The operators are binary tournament selection operator, single point crossover, bitwise mutation, and mu plus lambda strategy. So since it's a 4 variable problem, so we cannot show the simulation how the solutions are moving towards the optimum, but we can see the progress. So this particular plot shows that there is a drastic change in the fitness value, and then after close to say 45 generation, the improvement is very less. So we'll see this particular progress now. So here the improvement can be seen in the early generation of binary coded GA, and once it is reaches to 45, the improvement is there is no improvement. Then afterwards, somewhere close to 140, there is a little improvement. Close to 170 also, we have a little improvement. Important point to note that still we have run this binary coded GA for 200 generation. The optimum solution is not found by this algorithm. Let us move to the second problem, which is Hamel-Blau function. This Hamel-Blau function is made of two variables. Now from the equations you can find that this is a nonlinear function. The value of x1 and x2 are lying between -5 to +5. So let us look the Hamel-Blau function. So the surface you can see, and when we draw the contour of this Hamel-Blau function, you can see there are 4 areas where the minima is lying. So Hamel-Blau function is a multimodal function. As I have mentioned on the right hand side, it has 4 optimum solutions. So all the 4 optimum solutions are also mentioned. Say one is at 3.2, another is at -2.8, 3.1, then another solution is at -3.78 and -3.28, and the last solution is at 3.58 and -1.848. And at all these 4 solutions, the function value is 0. Now we are using the binary coded GA. Since it is a multimodal problem, we are keeping the population size 60. The number of generation is kept little high, which is 200. To have more precision, we are taking x1 binary string length for x1 20 and binary string length for x2 is also 20. So overall chromosome length is 40. Probability of a crossover is 1 and probability of a mutation is 0.5. We perform the same set of operators such as binary tournament selection operator, single point crossover operator, bitwise mutation and mu plus lambda strategy. Now this is the first generation in which the solutions are generated randomly throughout the range of x1 and x2. So let us look at the simulation now. So the simulation here, you can see the solutions are divided into all the 4 optimum solution, around all 4 optimum solution, and slowly they are converging to the optimum solution. So in the during the iterations, the solutions are distributed in such a way that they got all 4 optimum solution in case of binary coded GA. Please note that in this case we got the 4 optimum solution with this simulation, but it is not necessary, because to have the solutions distributed among the peaks, we should use some methods called fitness sharing. Let us see the progress of the simulation on Hamel-Blau function. Now there is a drastic improvement, and close to 25 generations we have reached to the optimum solution, and then since we have reached it, so there is no improvement. So it can be seen that even though it was a multimodal problem, the binary coded GA was able to solve this problem quickly and generated the optimum solution in very few generations. The third example which we have taken is the rastrogen function. This function can be represented in n number of variables. Now since these terms are added into the objective function, this will create lot of local minimas. All the variables are lying between -5.12 to +5.12. Now for 2 variable rastrogen problem, you can see the surface which has lot of ups and downs or peaks or valleys, and if we see the contours at the bottom, you can see there are lot of local optimum solutions. Now the optimum solution for this problem is lying at the origin, and the function value is 0. Now the Rastrogen function here, since we have a we are taking the 2 variable problem, we keep the population size 60, number of generation 200, the length for x1 and x2 20 and a 20. So the chromosome string is 40, probability of crossover is 1, probability of mutation is 0.5, and the same set of operators we have used it. In this figure, you can see that the solutions are randomly distributed in x1 and x2 plane. So let us see the simulation for this problem. Now you can see the solutions which are distributed now moving towards the optimum, not only optimum, to the local optimum solutions as well. Now in the focused view, now you see that the solution, one solution was created close to the optimum, and eventually the other solutions are also moving to the optimum. Now we cannot see the red dot. It means that the optimum solution for the Rastrogen function is found by the binary coded GA. Let us see the progress. Now in this case, again there is a improvement in the fitness value with the number of generations, and in less than 60 generation we are quite close to the optimum, and then we are searching, and finally at just before 180 generation we got the solution which converges to the optimum solution for the Rastrogen function. We will take another case of Rastrogen function where the number of variable is 4. We take all the parameters. Here please note that we have written the binary string length of x1 and x2. Since there are 4 variable, so we are taking 20 binary string length for all. So the chromosome string, so it is not 40, so the chromosome string will become 80 here. Probability of crossover and mutation are given, and other operators are the same as before. Since it's a 4 variable problem, we will be showing the progress. Now from this particular figure you can see there is a drastic improvement less than 30 generations, and then the fitness remains the same, and then there is a last improvement somewhere close to 160 generation. So let us see the progress while solving this particular problem, Rastrogen problem with 4 number of variables. So the improvement can be seen once it is reaches to 30, there is no improvement, and at around close to 160 we get another improvement. Note that the optimum solution for this problem is 0 0, and the function value should be 0, and in the after 200 generation still binary coded GA is unable to find the optimum solution in 200 generation. So we can try, if suppose we increase the number of generation and population size, we may able to solve this problem using binary coded GA. Come to the last problem, which is Ackley's function. It is written in the 2 variables as x1 and x2, and it's a little complex function, and the value, the upper and lower limit of x1 and x2 is lying from -5 to +5. Looking at the surface, you can make it out that this wavy kind of a surface is going to create lot of local optimum solutions. Now in this contours, on the x1, in the contour of x1 and x2, you can make it out various local optimum solution. For the Ackley's problem, the optimum solution is lying at the origin and the function value is 0. Solving this problem, the parameters of BGA is parameters are remains the same. So we kept population size 60, number of generation 200, binary string length for both the variables 20. So the chromosome string will become 40. Probability of crossover and mutation are mentioned, and the same set of operators are used. So this is in the generation 1. The solutions are distributed as you can see in the x1 and x2 plane. So let us look at the simulation now. Now the solutions are moving towards the optima. They are also stuck at the local minima. Now in 20 generation itself, the solution have reached to the reach closer to the optimum solution, and we have to see whether binary coded GA can solve the ECLIS problem or not. Now see that the blue point is already on the red dot. Let us see the progress in this case. So there is an improvement, continuous improvement in the best fitness in the population, and that is improving. And after 40 generation, there is no improvement in the fitness because the solutions are generating, the selection is performing crossover and imitation, and somewhere close to 130 there was improvement in the population, and that's why the best fitness was improved. So let us see one more time. So closed at 130, the solution has improved, and there is a little improvement after 170 generation. So with this we have come to the closure of module 2, that is based on the binary coded GA. So in this module we have understood the algorithm, and we have gone through the example by following the generalized framework. So we started this binary coded GA while showing the solution representation. In that one, the binary string was used to represent the real variable. The working principle of binary coded GA was shown with an example of Rosenbrook function, and in that example we have evaluated the function. So first the binary string is decoded and x1 and x2 values were calculated. Then after calculating the fitness, selection was done, crossover and mutation was performed, and finally survival stage was used to select the best solution. So the same hand calculations were shown in the graphical example. In this session we discussed more operators, especially we target selection operator, crossover operator and mutation operator. Since they work in a different way, their performance also will be different when we solve a problem. Finally, the application of binary GA on mathematical problems, we have taken 4 mathematical problems, we have shown those performance, and we found that as we increase the binary string length, the solution which is generated by BGA, it is closer to the optimum solution. However, when we increase the number of variable for say Rastrogen function and Rosenbrook function, binary coded GA is still little far from the optimum solution. We may require a larger population size as well as more number of a generation to get an optimum solution. So with these remarks, I conclude module 2 on binary coded genetic algorithm. Thank you.